All right, let's start. Do you have any questions? All right. So I guess let's continue with the problems for 4.4, or just the problems in chapter 4. And so far, right, we've done question number 22, sorry, 20, 22, 24. No, not 24. 26, right? Where the theme here, right, is from problem 4.20 that says that basically, okay, so first of all, right, it says that if you have a doubly, right, a stochastic process, meaning that, the sum, right, over the columns. So for a fixed column J, right, so sum over all I is equal to 1, right? If we have some transition matrix like this, then the stationary distribution, right, with m states, right, or I guess m plus 1 states, right, 0 up to m, then the stationary distribution, right, pi p equals to pi, satisfies pi I equals to 1 over m plus 1, right, for all I. I mean, of course, whether or not it's, what do you call it, like irreducible, right, is up to the matrix itself, but we can apply the theorem 1 and theorem 2 to a doubly stochastic process if we can check in addition that it satisfies, right, the other conditions, that is irreducible, right, and aperiodic. But basically, so the point is, right, in a lot of the questions, right, to apply theorem 1 and theorem 2, if you recall, basically, right, both of these tie the long-term distribution, sorry, long-term proportion, right, with the limiting distribution with the stationary distribution, which is the one that solves pi p equals pi, sum over pi I equals to 1. So basically, there's some conditions to check here, right? Like, for example, here you need to check that it's irreducible. Here you need to check that it's aperiodic. But all in all, it's really about, right, solving this equation. And the challenge with solving this equation, as you can see, right, with these problems, is that P may be hard to describe, right? P may be inconvenient. Let's say hard to write down, right? So this is a statement in general, right? That what you can describe as stochastic process, or you can describe a Markov chain, where P, I mean, it's quite intuitive what the Markov chain is doing, but you want to write down the explicit P, the transition matrix, is not that simple. Then, right, something like doubly stochastic process, well, there are other techniques, but one of the technique, right, well, is to check, and again, it's by luck, right? Not by luck, but by looking at this Markov chain itself and see, right? Well, so again, what is this, right? Basically, I think most doubly stochastic process is pretty special somehow, right? Because it says that if you look at, right, so Pij, of course, is xt plus 1 equals to j condition xt equals to I, right? So basically, for a fixed state, you look at all states that go into it, right? So your analysis is about all states that goes into state I, and make sure, right, and somehow that the probabilities there, right, is always 1. So in some way, you kind of reverse the direction, right? You reverse the direction of investigation, right? Usually with Markov chain, we look forward, right? We look to move from I to J, but when you look at doubly stochastic process, you fix the state J and you look at all state I's that goes into it. So your view, right, is kind of backward. I mean, your attention is backward. So this kind of let's say taste, right, will actually be sort of a part of something called reversible Markov chain. Okay. Depending on how much time we have and depending on how I want to cover things, we may or may not look at reversible Markov chain, but it's a chapter, right? It's a section, time reversible, right? Markov chain. You can just read that yourself, right, and see what's going on there. Basically, the point is that you don't have to view time forward. You can also view time backward, and there's some benefit in doing so. Okay. Okay. So, all right. So with that said, I think let's do new problems. Okay. So I think yes, of course, quiz 1. Right, this is question 23. What was it? In a good weather year, let's just call it a good year. The number of storms is a Poisson 1. In a bad year, it's a Poisson 3. So a good year is equally likely to be followed by either a good year or a bad year, right? So, and then bad year twice as likely to be followed by bad as by good. Okay, let's write that down. That's a mouthful. Good is equally likely to be followed by good or bad, right? Bad twice as likely to be followed by bad as by good. Okay. Now, what does this tell us? This clearly, right, is about the transition matrix P that describes the good and bad states, right? Or you can just call it 1 and 0, right? 1 for good, V for bad, right? It tells us how the good and bad year follow each other, right? In terms of probability, okay? And then we suppose that we start with a bad year. Oh, sorry, we start with a good year. Okay. Find the expected total number of storms in the next 2 years. Oops. All right, so how do we do this? So clearly, right, it's just really about what? How the next 2 years play out, and you know, the expectation, right, of the number of storms in each of those years. So if we have 0, right, then we could have what? 0 follows by 2 zeros, right? So which will be 2, right? You know, we understand what this means, right? Basically, first is 0 followed by 2 zeros, and then we can have a 3, right? Which is a times 2. It's incorrect, right? So I think because 0, 1 may be different from 1, 0, right? And then we can have 2 good years. Sorry. This is 6, right? And this is 4. And then 2. Right? Agree? And so, well, what is that, right? So, oh, by the way, right, how does the matrix P look? So if you look at 0 as good, sorry, 0 is bad and 1 is good, then you have what? Well, a good is equally likely to be followed by good or bad. So 1/2, 1/2. Bad twice likely followed by bad. So it's 2/3, 2/3, 1/3, right? So here, bad to bad and bad to bad. So it's 2/3 squared, right?
We suppose the year 0 is good, right?
Uh, no, thank you. I mean, I'm confused between year 0 and what we call as good. Sorry. No, appreciate conditioned by 1. Yeah. No, my bad. I mean, year 0 and I call it just 1, right? I should call it GGs to you know what? I think, yeah, with what you said, maybe I should just switch notation. Uh bad, right? Bad, good, and good. And let me just switch this. Yeah. So bad, good. This is whatever, right? Bad, good, 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 bad, good, and then good, good, good. Yeah, thanks. So, okay, hold on, right? So this is what? Good to bad. So that's 1/2, good to bad, and then bad to bad, right? So 1/2 times 2/3, right? And then good to good, and then good to bad, right? And then I think the other one's the same. And then finally, sorry, this one's not the same, right? This is good to bad, and then bad to good, which is 1/2, 1/3. And then good, good, good is 1/2 squared. All right. All good. Any question? All right. B, find the prop that there's no storm in year 3. Well, so there will be no storm in year 3 if what? So there will be no storm in year 3 if well, it depends on what year 3 is, right? So if so it'll be, you know what? So this is the right answer, right? But I think I want to do something a little bit more formal. So this is fine, but before this, right? I want to do this. I want to kind of actually go back and say, right? So if we let X, right, be the state, right? Good or bad? State of the year, right? Like good or bad. And if I want to let YT, right, be the number of storms of the year, right? Then what's given is that YT condition on XT equals to good is Poisson, right? 1. And YT condition on XT equals to bad is Poisson 3, right? Okay. So what can be done a little bit more, let's say, rigorously here, is to look at expectation of Y1 plus Y2, right? The number of storms in the next 2 years. And which will be, right? So expectation of Y1 will be expectation of y1 condition on the state of x1, right? So that will be, so y1 will be 1, right? Expectation y1 will be 1, right? Times probability that the first year is good, which is good times good, which is a half, right? So hold on, let's say this, right? So expectation of y1 plus expectation of y2, right? And expectation of y1, so let me write here. An expectation of y1, right, will be 1, right, times probability of first year is good, which is a half. And expectation of y1 is going to be 3, right, times the probability the first year is bad, right, which is good to bad, right, which is a half. Right. And then expectation of y2 will be 1. And then if the second year is good, how can the second year is good, right? And the second year can be good if we go from good to good, which is a half times half. Or the second year can be good if we move from good to bad to good, which is good to bad is a half, and then bad to good is a third. Half times a third. Right, like that. And then it can be a bad, right? If you move from good to bad, which is a half times 1/3. So a half times 2/3, right? Or it can move from good to bad, right? Which is also, so good to bad is, so good to bad, or good to bad. So this is good to bad, and then good to bad is 1/2 squared. Okay, like that. Now, if you compare this answer with this, right, they should be the same, I hope. Is that true? So 6 times 1/2 times 1/3. We have a 1/2 times 1/3 here. One second. So this approach kind of take the sum together and multiply, while this takes the expectation of each. I just want to make sure that they give the same answer. You know what? I'm not so sure about this. So let's cross this out. I'm not so sure about, I think intuitively they're the same answers. I just don't have time to verify this too. This is pretty sure this is correct because we separate out, right? The number of storms at the first year, number of storms at second year. The problem with this calculation is that it lump, right, the expectation on each year together times the probability, and that might be the wrong calculation. So yeah, I would say that I don't trust this, and this should be the right calculation. I mean, there's a chance that they're the same, but let's not spend time on that. All right. Any question? Okay. So now let's move on to B, right? Probability that no storms, right? In year 3. Okay. So, right, basically this is probability at Y3 equals to 0, right? And Y3 will be, right, Poisson 1 or Poisson 3, right? Depending on the year. So at this state, I think it's not possible to write down the sequence. So it'll be something like this, right? It's going to be e to a minus 1, right? Which is the probability that Poisson 1 is equal to 0 times p cubed, right? And you move from good to good. Or it's e to minus 3 p cubed, and you move from good to bad, like that, right? So that's probability of no storm in year 3. Is that okay? Right. So C, long run average of the number of storms each year. How can we do this? So basically, right, intuitively, what would this be? Intuitively, this should be so 1, right, would be the number of storm per year times the long-term proportion of good years, right? And then it's going to be 3 times the long-term proportion of bad year. Okay? Which really, right, is the language of pi g, right? 1 times pi g plus 3 times pi b, where pi g and pi b satisfies what? Pi g times pi b, right, multiply with, sorry, it's 3 pi b pi g, right? Because we say good first, bad first, good later. Right, and then it's 2/3, 1/3, right? And 1/2, 1/2 equals to pi b pi g, right? And if you solve for this, we will get, well, let's see, 2/3 pi b plus 1/2 pi g is pi b, and then 1/3 pi b plus 1/2 pi g is pi g, right? Of course, they sum up to 1, right? So what would this be? If you add both of these, we'll get, no, adding is not good, right? If you subtract across, then you got 1/3 pi b is pi b minus pi g, right? Or pi g is 2/3 pi b, right? In other words, what's the probability? So if they sum up to 1 and pi g is 2/3 pi b, well, pi b plus pi g is 1 plus 2/3, right? Pi b is 1. So that's going to be 5/3, right? So pi b is 3/5. Pi g is 2/5, right? And so there you go, right? If you plug those in, you get the long-term proportion. Any question? All right. The long-term proportion. Sorry. Yeah, it's just a proportion, right? Proportion of years with no storms. What would that be? So intuitively, right, the long-term proportion of good years is good, and the long-term proportion of bad years bad. Each of them, right, has a probability of no storm. So the long-term proportion of years with no storm is just the long-term proportion of good and bad years times the probability that those years have no storms. So it'll be 3/5 times e to minus 3 plus 2/5 times e to minus 1. Right? Any question? All right. So what's the lesson here? Well, the lesson here, of course, is first of all, it's the wrong calculation I did here, right? That we need to kind of write down clearly what we are calculating the model. If we don't, we can lump like the calculations, right? The numbers together and then multiply with the wrong probability. I am pretty convinced that these are not the same answers now, right? And this is wrong because it's just I don't know, you think about it. Basically y1 and y2 cannot be lumped together in the same calculation. But on the other hand, right, notice that the question here has a lot to do with, let's say, y, right, the number of storms. So let's just ask a side question. Is YT, right, the number of storms per year, a Markov chain? Right, is the number of storms in the year T a Markov chain? Well, you see, the answer is no, right? The reason is because given, right, let's say the number of storms in the previous year, it's not possible, right, to say what the number of storms in next year is, because you don't know if it's going to be a bad year or a good year, right? So the point is, well, but on the other hand, right, notice that the questions that we've been asking are all about y itself, right? So why is that so? Or for example, right, let's say part D, long-term proportion of years with no storms, meaning the long-term proportion of years with YT, right, being zero, right? Long-term proportion of years with YT being zero. And you see, right, the thing is that YT itself is not a Markov chain. And we, of course, right, piggyback on X, right, the good year and bad year to solve for the questions. What that means is with the XT itself, then we can determine. In other words, actually, this is an example of enlarging the state space. I mean, of course, XT itself is a Markov chain, that's clear, right? That's given, the state of good or bad, that's given in a problem. But if you tag along the Y itself, YT, XT is also a Markov chain. Well, why, right? If you know the previous year is a good year, then you actually can determine, right? So in fact, the Y is just tagging along, right? The X really is the information giving, but YT is like, you know, some process, right? With in some, I think in some model, XT is called a hidden Markov chain, meaning that actually, right, in real life, what you observe is you observe the number of storms, right? You don't observe X, you don't observe that a year is good or bad. So in fact, right, this is sort of like a model is, you know, in reality, what people study is if you observe the YT, knowing together that YT depend on XT, right, the state, then to be a Markov chain, then how can you kind of deduce, right, the state of XT by observing, right, the sequence of YT, right? For example, you observe the sequence of storms in the last 20 years or so. Can you find out the good year or bad year? And can you find out, or can you estimate the transition matrix, right? That allows you to move from a good year and bad year by observing the sequence of storms in the last 20 years or so. So that's sort of like the point of this question. This is the model, but what we observe, right, we don't observe the good year, bad year. We observe the number of storms. So statistically, we want to deduce this matrix rather than this being given. All right, all good? Okay. So second question. This is question number 24. So we have 3 urns, 1 red, 1 white, 1 blue. So the red urn contains 1 red and 4 blue balls. White urn contains 3 whites, 2 reds, and 2 blue balls. And then the blue urn contains 4 whites, 3 reds, and 2 blue. Okay. So initially, meaning as step 0, right? A ball randomly selected from the red urn and return to it. But after that, basically, right? So the scheme is pretty simple. So the urn has colors that are the same as the balls, right? And you would look at the color of the ball selected from the urn previously, and then you would go to the urn with that color, right? And keep selecting the ball. Is that okay? So after that, ball will be selected from the color from the urn, right? With the same color as the previous ball selected. And return, right? And so there you go, right? You just keep sampling balls, but then the color of the urn you pick will be from the previous balls, right? You pick. And the question just asks for long-term proportion of red ball you pick, white ball you pick, and blue ball you pick. So how do we do this? So, right, this is clearly just a question about solving for pi p equals to pi, right? Where p is the transition matrix that tells you how you would move from red, white, and blue balls to red, white, and blue balls, right? Or, or urns, right, for that matter, because red, white, and blue balls will correspond to red, white, and blue urns, right, that you select from. So, doesn't matter. Okay. So, can we fill this out? For example, right, what's the probability we go from red to red? If a previous selected ball is red, right, then you will pick a red ball with probability 1/4, right? And then, sorry, 1/5. And then 4/5, right? If the previous ball is white, then you would go to red, accordingly, right? So it's 2/7, 3/7, and then 2/7, right? And then similarly, you have 3/9, and then 4/9, 2/9, right? And you just solve for this. It's probably a boring calculation, so we'll skip that, right? But yeah, right, it's just solving for this pi p equals pi. So just to be clear, right, on the exam, if there's ever a question about solving, okay, for pi p equals pi, like numerically, well, you know that you do have to write down a matrix because that's to show that you know what matrix you're talking about. But if you have to solve for pi p equals pi, technically speaking, you don't have to, or I won't demand that. Meaning that you can say, suppose the solution to this is that, so then you can call pi 0, pi 1, pi 2, or you can call it pi r, pi w, pi b, right? And then proceed to use it as if you have solved for it, right? Meaning I don't require you to solve for the eigenvector as long as you have the matrix written down. And as long as the eigenvector exists, right? Because who knows, maybe there's a transition matrix that doesn't have, right, a stationary distribution. Then if you don't recognize that and you say there's such a vector, then of course it's wrong. But if there is such a vector, then you can go ahead and use it without solving for it. Is that okay? Any question? All right. So let's move on to the next question, which is question number 25. So each morning, somebody go for runs. So the person has the house as equally as back and front door. So to leave either at back or front door. So upon leaving, the person just choose a pair of shoes. So basically, I think the context, right, is that the front door and the back door have shoes, right? I guess, or technically speaking, pair of shoes, right, placed there, right? And the person just choose a pair of shoes to run or barefoot, meaning no shoes, right? No shoe is an option. If there's no shoe. So, and then the person would return in the same way, meaning equally likely, right, to be at front or back. And then would leave the shoes there if he runs, if he has the shoes, right, and leaves the shoes there. So, right, is that clear? Basically, right, it's just basically back and forth, right, between, not back and forth, but so the person would choose, right, one half in the morning, let's say, and then pick up, right, the shoes there, and then choose one half to return, and then would leave the shoes there, right? So the person owns K pairs, right? Proportion of times he runs barefooted. That's the question. So we understand what this is saying, right? So basically, for example, right, you have 3 and 7 here, right? Then by choosing a half, right? Say you choose here, and then you could return here, right? And then it'll move to like a 2-8, or it could say it's 3-7, right? And so on and so forth. And then at some point, it might turn to 0 and 10. And if you choose this, then you run barefooted. But you could have chosen this, right? So you won't run barefooted, etc., etc. And so the question is, right, the proportion of times the person runs barefooted, meaning the proportion of time the person goes out of the door with 0, right? Shoe. So how do we do this? So first of all, right, this clearly has something to do with a Markov chain. But what Markov chain do we want here? And so more importantly, right, if you want to look at Markov chain, you have to kind of see what is modeling, what is tracking. So what are we tracking here? So I think maybe a challenge to a problem, or maybe it's kind of the danger to a problem, right? Is that it's tempting that you want to watch the whole thing. You want to keep track of both doors. Okay, front and back. But you see, it's kind of hard because well, not hard, but it's kind of complex because you have to say, well, 3-7 here moves to either 3-7 or 2-8 or 4-6, whatever, right? And that's what a lot of things to keep track of. On the other hand, notice, right, that no matter what the states are on both of these, they all have to sum up to the total, which is 10, right, or K, right? In other words, actually, you have to only track one door. I mean, of course, we have to kind of figure out what that has to do with the proportion of times he runs barefooted, right? But, right, if you just want to track the state of shoes on both doors, which is clearly, right, the information we need to answer the question. We only need to track the number of shoes at one door. The other one will be K minus that. So pick your favorite, right? Doesn't matter. So you can say, let's say XT, right, is the number of shoes, right, in the morning, right, before the person run, let's say, right, on day T, right, at front door, all right? So let's see that we can, if this is a Markov chain, and if it is, then, right, K minus XT will be a number of shoes in the morning, blah, blah, at the back door. Okay. And so can we write down the transition matrix of XT? Or is XT a Markov chain? What's the transition matrix? So what states can XT take? Clearly, right? 0 to K. 0 to K, right? XT can be from 0 to K. Now, where can XT move? Let's say you are at state I, right? Meaning you have I pair of shoes at the front door. What can that go to? You see, if you think carefully about it, right? If you are at state I, you can only move to what? I plus 1, I minus 1, or I, right? On next state, which is tomorrow, right? How? I mean, wait, hold on. Yeah, right. You can move to I plus 1 if the person leaves at the back door, right? And then return the front door. You can stay at I if the person leaves at front, goes back at front, or leaves at back, goes back at back. And then here is, of course, right, leaves at front, but it goes back at back. Agree? So that's true, right? Except for state 0, of course, where you only have forward, right? You cannot decrease, right? So something like this, right? Probability xt plus 1 equals to I, condition xt equals to I will be, so this is for I, not 0, right? And not K, right? This will be 1/2, right? And then I plus minus 1 is 1/4, right? On the other hand, for state 0, then you can either go up. Sorry. What kind of probability? Well, if you're at state 0, right, you'll go to 1 if you go from the back and return, right? That's it, right? Because if you go from the front, you guarantee to stay at 0, right? Because you will have no shoes. So, hold on. Yeah, okay. So this is 1/4, right? And then this is 3/4, right? How? You either go from the front and return anywhere you want, because, right, you go barefooted now, or you can go from the back and return the back, right? Which means you also have 0 shoes in the front, right? And similarly, right, if you are at K, right, then this should be a quarter, right? Am I right? I hope. So if you have K shoes at the front, right, then it will lose one shoe. Hold on, maybe this is wrong, right? You will lose one shoe if you go out in the front and go back in the back, right? Yeah, I think it's true, right? One quarter. And then you will stay the same. Oh, sorry, equals to K, right? If, right, under any other scenarios, such as go out in the back and go back. If you go out the back, right, it's guaranteed that it will stay the same here. Or you can go to the front and return to the front. So that's 4 quarters. So that's the transition matrix. Okay, so far. So now what do we want here? We probably want the proportion of time that the front door has no shoes. Notice, right, this is not the same as proportion of time the person run barefooted, but it's connected, right? So let's look at that. Proportion of time the person, sorry, the front door has no shoes, right? So this is, right, the pi zero, where, you know, we have the pi p equals to pi, right, system, where, right, this is p, right? So, you know, true to what I said, I don't care to you solve this. You can just call it pi zero. However, right here, can we do better? Can we say what pi zero is? Is there any hope? Is there any chance to say what pi zero is? So here, I would just spend, let's say, 1 minute to check if P here is doubly stochastic, right? Because the structure of like only from I moving to 3 consecutive states is quite easy to result in a doubly stochastic, right? You know, process, transition matrix. So it's just, let's check real quick if that's true. So 0, right, goes to 1 with 1 quarter. Sorry, 0 stay at 0 with 3 quarters, right, and 1 quarter, right, and the rest is zeros, whatever, right? And then 1 would stay at 1 with 1/2, and then goes 1 quarter, 1 quarter, right? And next we'll have 1/2, 1 quarter, 1 quarter. And you see, and next we'll have 1/2, right? It'll shift like that, right? You see that this is 1, this is 1, and this is 1, right? So it's doubly stochastic from just looking at the matrix visually. But if you want to kind of check in terms of the equation, right? Again, think of it, right? If you have a state state J, right? meaning you have K shoes, right? You have J shoes at the front door. How many states can go into J? Well, clearly there are 3 states that can go into J, right? Either J minus 1, J plus 1, or J. Only these 3 can go into J, right? J can go into J with probability 1/2, right? J minus 1 can go into J, well, which is the same as, right, this one. So 1/4, 1/4. Notice, right, it's reading this backward, and of course you have to check the special case of 0 and K, but either way, P is doubly stochastic. Therefore, right, pi 0 is 1 over K plus 1. Okay, so far? And so now, right, we know the proportion of time the front door has no shoes. Then what's the proportion of time the person runs barefooted? What would be? So here's front, right? Here's back. Proportion of time, right? The front has no shoes is this. But notice, right? If one door has no shoes, the other one will have K pairs, right? So the person will have no shoes if the front door has no shoe and they choose a front door, with probably 1/2, right? Or if the back door has no shoes, which means the front door has K shoes, and they choose the back door, right? Now, I guess the problem is a little bit more interesting if you have like, I don't know, 1/2, 1/3, 2/3 to distinguish, right? But I guess if that's the case, then this matrix will be changed and we might not have a doubly stochastic, right, matrix. But as it stands, the answer is 1/2 times pi 0 plus 1/2 times pi K, which really is just 1 over K plus 1. Okay. Well, 1/2 times pi 0 is because of the front door having no shoes and the person chooses a front door. Notice the pi K is still referring to the front door, right? Or the front door has K shoes and the person chooses the back door, right? Like that. Any question? Okay, let's continue. All right, where are we? This is quiz 3. Let's look at quiz 4. This is question number 34. So a flea moves around the vertices of a triangle in the following way. Whenever it is at vertex I, it moves clockwise neighbor with probability pi. And counterclockwise neighbor. Of course, right? Yeah, so not of course, but so 1 minus pi, so it won't stay at the same vertex, right? So I don't know, maybe something like this, right? So you can call it 1, 2, 3 if you will, doesn't matter, right? So, well, what's clockwise? Clockwise is this way, right? And so 1 will move to 3 with P1, P1, right? And then this is 1 minus P1, right? And this is P2, 1 minus P2, and then P3, 1 minus P3, right? So far, so good. All right, so question A, find proportion of time. The flea is at each vertex. Well, we know what this means, right? This is solving for what? Pi p equals to pi, right? Where P is what matrix? P is that matrix, which is kind of written down in terms of the picture, right? 1, 2, 3, 1, 2, 3, right? 0, 1 goes to 2, 1 minus P1, P1, right? I mean, of course, here you kind of have to give the picture too, because you might call 1, 2, 3 in a different way, right? So I happen to name 1, 2, 3 counterclockwise. Who knows? But someone can name 1, 2, 3 clockwise, so will have a slight different, right? Transition matrix than I do, but 2 goes to 1, P2, 2 goes to 3, 1 minus P2, 3 goes to 1, 3 goes to 2, right? Like that. Okay. And then, I mean, I don't know. Writing down a solution like this is a pain, but let's just say we have that, and that would be the proportion of time, right, at each vertex. Any question? Then I guess, right, question B might be more interesting. How often does the flea make a counterclockwise move and then followed by 5 consecutive clockwise moves? What does this mean? So if you remember, right, the point is we talked about how if you have, right, pi 0, right, pi I, pij, this will be what? A long-term proportion that you spend at state I and then immediately move to state j, right? Notice, right, the catch is that you must have pi I here. If you just have pij as the answer, that's wrong. Pij is the conditional, right, probability that you move to state j condition on your state I. Or you can say it's proportion of time you move to state j knowing you are state I, right? But in general, if you don't know where you're at, then you have to multiply with the proportion of time you spend at state I as well, right? If you look at the long term, because in the long run of the whole run, you do not know where you are, right? So anyway, here it's exactly like that. It's just more painful to write down, right? Let's write down one of them. For example, you can have pi 1. If you're at pi 1, right, then you do a counterclockwise move by moving to 1 minus pi 1. And then 5 consecutive moves. So that will be sorry, 1 minus p1. And then you can have p2, p1, p3, p2, p1. Right? And then you can have pi 2 times 1 minus pi p2. And then you will move back, right? So you have p3, p2, p1, right? p2, 3, p2, p1, p3, p2. And finally, you have pi 3, clockwise is 1 minus p counterclockwise, and then you'll be at p2, right? So you can have p2, sorry. Hold on. You'll be at p1, right? Sorry. So p1 and then p3. And then p2, p1, right? p1, p3, p2, p1, p3, p2. Like that. All right, any question? Okay. So let's continue. So this is question number 35. So we have a Markov chain which states 0, 1, 2, 3, and 4. Suppose we have P04 is equal to 1. And suppose if you're at a state I positive, the next state. So, okay, from 0, you have to go to 4. But for any other state, it's equally likely. But up to I minus 1. Okay. So I guess you have to pay attention to that up to I-1 only. And they ask for find the limiting prop of this Markov chain. Okay. So again, right, what are we dealing with? Well, we have to write down what the matrix P is, right? And then solve for pi P equals to pi. But this P might be a bit special, so let's take a look. 0, 1, 2, 3, 4. 0 guarantees 0 to 4. State 1. Equally likely from 0 to I-1. So I think 1 is guaranteed to go to 0, I believe, if we read I-1 strictly. Then 2 is 1/2, 1/2. 3 is 1/3, 1/3. 4 is 1/4. Like that, right? So 1 is guaranteed to go to 0, 0 guaranteed to root 4. The rest are like that. And then, so you're supposed to solve for pi P equals to pi. I suspect that, this structure, right, is really a kind of a lower triangular, right, with this. It probably has some, easy equation going on there. But yeah, I'm not super interested in solving this. So let's just say that that's that, whatever that is. All right, any question? I mean, I think in the solution, you'll see that I solved for this, but right now, let's not waste our time, right, solving this boring thing. Okay. Quiz 6. That's question number 37. Show that the stationary probabilities or stationary distribution of a Markov chain with transition matrix P is also the stationary distribution for a Markov chain with transition matrix. Q, which is P to a K, for any positive integer K. So what are we asked to show? We're asked to show that if pi P equals to pi, right, then pi Q equals to pi, where Q is P to the K. But that's super obvious, right? Because if you just multiply p at k times each time, right, this doesn't change pi, so k times it doesn't change pi, so it's equal to pi, right? So that I would say that's super obvious. Any question? All right, so number 39, we have discussed, that's the question about the symmetric random walk being non-recurrent by showing that the stationary distribution is 0, right? So let's move to question 40. It says that a particle moves on 12 points on a circle, so like a clock, right? At each step is equally likely to move one step clockwise or counterclockwise. So actually, it's really a symmetric random walk on a clock. One step. So this is really a symmetric random walk on a clock, right? Find the mean number of steps. For the particle to return to its starting position. Huh. All right, so what are we dealing with here? So, I mean, first of all, it's clear that this is a Markov chain. So some Markov chain stuff is required, which means we would probably, right, need the transition matrix. So just write it down, first of all, right, and see what happens. So the only thing, right, is this transition matrix, 0 can go to either 1 or 11, right? I mean, 1 to 12, whatever, if you want, right? 12 being 0, right? So like that, right? And then 1 is 1/2, 1/2. Right, so on and so forth. 11 can go to 10 or go to 1, right? So first of all, what do we notice? We notice that this is doubly stochastic, right? Again, why? Because how can you go into a state? You can go to a state by just two directions, right? Being adjacent to those states. Each has 1/2 probability each. So meaning, right, that each of the pi's will be 1/12, right? So that's there. But is that what's being asked? Find the mean number of steps. So what? What is that? What is that object that's being asked? So the mean number of steps, right? Remember, we'll talk about the first time, right? To go back to any state, which if you remember exactly is that concept of tau I. Tau I is the first time that you go back to I condition on start I, right? And what is the relationship between tau I and pi I? Remember, pi I is 1 over tau I expectation, right? Why? Because for every tau I steps, there's one return. So the proportion of time that you spend at the state is exactly 1 over the length of time, right? So pi I is really like a rate, right? So there you go. But here, because everything is 1/12, so therefore tau I expectation will be 12. So takes 12 steps to return to its starting position on average, which of course makes sense. Any question? All right. Let's continue. Quiz 8. So this is question number 46. All right. So an individual with R umbrellas go from home to office and vice versa. So it's actually very much like the shoes problem, maybe a bit more sophisticated, right? So let's just say, let's describe in a picture. I think it's easier than to write down the whole thing. So basically, our umbrellas, right? So the total number of umbrellas, right, is R. So I don't know, again, like 3 and 7, right? Let's say 3 umbrella at home, 7 at office. It could rain or shine, right? Rain or not on his trip, right? Home office. If it does rain, he'll take the umbrella, if there's one. If there's no rain, he won't take the umbrella. All right. So there's 2 conditions that he will not take the umbrella. Of course, if there's no umbrella to take, he'll just be wet. But if it doesn't rain, he also won't take the umbrella, right? Rain on the trip. And then there's an umbrella to take. All right. And so rain here is flipping a coin. So lucky us, right? You can imagine that the rain can be a stochastic, can be a Markov chain, right? Rain, not rain, whatever. But here it just say rain is an independent coin flip. So rain with probability P, ouch, on each trip. right? Independent of the past. So technically speaking, the book says something along like he goes from home to office in the morning, go back from office to home at the end of the day, blah blah blah, right? But you can just think of a trip here, trip there. Of course, right? He will have to make a trip from home to office and then office from home, right? Each step. All right. And then there's a rain condition would probably P. Okay, so far? Other question. So we want to determine the proportion of time the person gets wet. I mean, wet means what? Wet means it rains and he goes out without an umbrella, right? On either trip, right? That's, I guess, the big theme, but then they break down the questions for you to solve along. But let's just write down. Okay. But I guess part A, it just asks you to define a Markov chain with R plus one states to help us deal with this. What would that be? So the Markov chain we're looking at clearly is the one that tracks the number of umbrellas, right? Either at home or the office, doesn't matter, because the other one would be R minus that, right? So let's say XT is the number of umbrellas. Let's say, notice, right? He goes from home to office in the morning and office from home at night. So it's just like before the morning or something, right? He will not take the trip from home at night, things like that, just to make the language easy. Number of umbrellas at home, right? Each morning, right? Before he leaves, right? Okay. And then, of course, R minus XT. Uh, you know what? It's not quite the same, right? The reason is how to say it's so here's the thing. Yes, so XT is number of umbrellas at home each morning before leaving for office. But then by that token, R minus XT will be number of umbrella at the office in the morning though, right? Because if you want to look at the office state, right, it will depend on what action he takes, right, when he leaves home, which of course depends on the rain condition. So but I think I just got disconnected, right? Let me share again. Okay. Can you hear me all right? Can you see everything? Did I miss some of the part of the lecture I didn't quite know that I got disconnected with? Everything's okay, right? So YT's number of umbrellas at the office each evening before leaving for home. Just to make sure I'm not kind of speaking to myself here. Can everyone hear me all right?
Yeah, I don't think anything was missed. It was just gone for a second.
Okay, appreciate it. Thank you. Um, so cool. So basically, XT and YT is not really right. R, right? So it's not really that XT plus YT is equal to R. The reason is because, right, there's a time gap. It's similar, right, to the running shoes problem, but there's like kind of like a transition, right, from home to office that we need to take care of. So something like this, right? YT will be XT plus 1, right? With probability, well, if there's a shoe, okay. So let's say condition on XT not equal to 0, right? With probability P, right? Because he will take an umbrella to the office if there's an umbrella to take. Ouch, 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 sorry. It's not XT plus 1, it's going to be what? R minus XT, right? Plus 1, right? Condition of XT positive with probability P, right? Like that. Which makes sense, right? You see, if XT is equal to 0, then R plus 1 will be more than R, right? He only has R umbrellas, right? So something like that, right? Of course, is equal to R if XT equal to 0, right? Regardless of something like that. Is that okay? So, but either way, right? I mean, if we can track XT, we can do YT, right? But so let's say that XT is the one we track, and YT is deduced. So part A, we will decide to track the number of umbrellas at home each morning before he leaves. Okay. Um, part B says show. Oh, you know what? We need to write out what P is, right? So what is P? So 0 up to R, right? What happens here? So if he has 0 umbrella, then how will he end up with 0 umbrella next morning? Well, he will, of course, go to the office, right? So home, office, right? If he has 0 umbrella here, he will go to office with no umbrella, right? We'll get wet, whatever, but we won't care. We'll look at that later. But then he will come back, and he will come back not bringing an umbrella if there's no rain, right? On the trip back, meaning that it's 1 minus P, right? And clearly, of course, the only other possibility is 1, right? Meaning that what? He will get an umbrella if on the trip back, right, it rains. Okay. what about one? If he has one umbrella at home, then you know it's same as the shoes, right? It can reduce to 0, stay at 1, or go to 2, right? Or goes to 2. So what? It can go, stays at 1 if he takes the umbrella and come back with the umbrella, meaning it rains on both ways, or he does not take the umbrella on the forward trip, right? So I think is p squared plus 1 minus p. 1 goes to 1. You know what? Maybe let us write down in terms of symbols, right? Probability xt plus 1 equals, so here we say 1, right? Condition xt equal to 0 is p. Probability xt plus 1 equals to 0, condition xt equal to 0 is 1 minus p, right? As we explained. Now, this is probability, so condition xt equals to I, right? This is I, is p squared plus 1 minus p for I from 1 to k minus 1, r minus 1, right? Okay. Let's see. What about he gains 1 umbrella? He gains 1 umbrella if on the trip home there's no rain, but on a trip back there's some rain, right? Notice that if it's 1 to r minus 1, he will have umbrella on both places, right? To take back. So that would be what? So rains, not rain on a trip, well, either way, right? Is 1 minus p times p. Right? And then of course the other one is if it does not rain on a trip going here, but sorry, it rains on a trip here, but does not rain back, right? So still p1 minus p, right? And we should check that these 3 numbers add up to 1, right? Is that true? P squared, I don't know, 1 minus p plus should be 1, right? I hope. P squared plus 1 minus p plus 2, p1 minus p. So now this doesn't look like it's 1. Did I do something wrong? Two p minus 2p squared. No, right? Something is missing. 1 second. So this seems fine. How can he stays at the same umbrella if it rains on both trips? Oh, sorry, right? Here cannot be like that. If it does not rain on the trip home, he won't take the umbrella home with me. He might take the umbrella back. So it also must not rain on both trips. So that's that. And this is equal to 1. Okay. Any question? And finally, right, if he has R umbrella at home, then it will stay at R umbrellas. If, right, so he has R umbrellas, so he can take 1 back, 1 forward, and 1 backward, right? If it rains on both ways. Now, sorry, hold on. If it, Yeah, if it rains on both ways, yeah. If it does not rain on the forward trip, then he won't have an umbrella at the office. So it doesn't matter if it rains or not, right? So this is clearly p squared plus 1 minus p. And then he will lose an umbrella if, right, it rains on the way forward, but does not rain on the way back. And yeah, right, these two add up to 1. Okay. So that's the transition matrix. Any question? Notice, right, even though we separate the home and office in terms of the time, the transition matrix for the office is exactly the same, right? It's just that the values they take are not the same, or it's not even R minus the other one, right? Because they're of the moment in time. But transition matrix wise is the same thing. Okay. All right. Part B. Show that the limiting probabilities are so pi I is Q over R plus Q if I equals to 0. 1 over R plus Q if I equals 1 to R, where Q is 1 minus P. All right, so how do we do this? So clearly, right, we need to solve for pi p equals to pi. Well, I mean, not solve, prove, right, because the solution is already given to us. Well, can we? Well, what does this mean? So remember, right, this means pi I is the sum of pi I pij, right, sum over all I. And so clearly, right, there are two things. So I guess, hold on. I think I wrote this wrong, right? This should be sum over 1. Pi I pij, if you sum over all, that will be pi j, right? I hope I did not write it wrong before, right? Pi j is a sum over pi I pij, right? Okay. So we need to check for what? If this is 0, right? Then what state can go into 0? The only state that can go into 0 is 0 itself, right? Or 1, right? 1 can go to 0, right? 0 go to 0 would probably 1 minus p. So it's a question mark. Pi 1 can go into 0 with probability what? P or minus p, right? Or is that true? We propose that this is Q over R plus 1. R plus Q, right? And that's Q, right? So Q over R plus Q times Q plus pi 1, which is 1 over R plus Q times P times Q. Well, so we got Q squared plus PQ, but Q squared plus PQ, right? Q plus P equals to 1. So that's true, right? Okay. And let's check in the interest of time, right? Let's just check one more, right? In terms of the pi I, right? For I between 1 and k. And the last one at R, right? You just check for yourself. Then what? Pi I, how can you go into I? You can go into I from pi I plus 1, right? But sorry, R minus 1. Hold on. Because it depends on what, sorry, I think I want 2 here. Because, you know, it could be the borderline state, right? Because I just want the middle states. So something like this. So if you are between 2 and R minus 2, then 1 over R plus Q, right, is pi I. And then how can you go into I? You can go to I by similar states, right? There's nothing like state 0, right? Or state R. Oh, you know what? Sorry. So here I can be R minus 1, that's fine. But the only thing is I don't want state 0 go into state 1, right? So I have to check state 1 carefully. Anyway, right? So here it will be what? This one, right? P squared 1 minus P squared, so P squared plus Q squared. But it's easy, actually, because it's the same number. Right, and we just check that these 3 numbers add up to 1, right? So these 3 numbers add up to 1, so that's that. So, all right, I'll let you check, right, for pi 1. The reason why pi 1 is special because 0 can go into 1 and 0 has a different value, right? But that's it. And then I think pi R is also special because R, right, only R minus 1 can go to R goes to R. So check this too, right? But let's skip that. So basically that's how you check it, right? See what fraction of time the man gets wet. How do we do that? So he will get wet, right? If he is at home, right? From home, and it rains, right? But what else? He could, so notice, right? We don't want to kind of jump into the Y state because that's kind of confusing. He's at home and it rains, no umbrella. But he can also be at home with all umbrellas, right? And it doesn't rain on a trip forward, but it rains on a trip backward. That's all we need, right? That's it. Of course, pi 0 and pi R are the ones that are given from the previous question. All right, any question? All right, if not, then I think it's a good place to stop here, and then we'll pick up next Monday.